Okay. Trying to go live again. This is annoying. Okay. Stream key. Alright. Stream right there. Okay. All right, so I'm back. We just started a new stream. I don't know what's going on. I think it's just crappy Wi-Fi in my basement. Very sorry about that. We'll hope that this holds up for the next 15 minutes. We'll try to get through what we can. Okay, so I guess we froze somewhere around me writing that f prime. The point is that we want to find points where the curves are possibly not smooth. And so, of course, one thing that could go wrong is that the f prime or g prime, those functions might just not be differentiable at some point. We're going to see very shortly why this is the right definition for smooth, because we're going to use f prime and g prime to get equations for tangent lines. But what can happen is that if x prime and y prime are simultaneously 0, you can still get some weird stuff that happens. If you think in terms of motion, essentially x prime and y prime, if they're both 0 at the same time, that means your x coordinate is paused, your y coordinate is paused. That means you've essentially come to a stop, right? Now, if you come to a stop, you can turn and you can start going in a completely different direction. And your motion is still smooth in a sense, but the curve you leave behind is not. You can have corners or cusps. So let me show you what this curve looks like. Now, we found that when t is equal to 2, right, and just also, let's see, what are the coordinates? If x of 2 is going to be 4 minus 8, x of 2 is minus 4, y of 2, looking at the original function, is going to be 8 minus 8 minus 8. Okay, we have something that looks like that. So if we were to plot that one in GeoGebra, then what we have is, here we are. I was working on it when I realized that everything kind of crashed and burned on us. So let's say we go t going from 0 to 4. Okay, interesting. Let's try, actually let me try a bigger range of values, minus 4 to 4. Okay. Yeah, let's do that. And now that looks perfectly smooth, but let me zoom out. See what's happening. Ah, there we go, right? You can see that point where it stops being smooth, or there's that cusp, right? So There's that cusp in the curve, that right down at this point right here, right? There's that cusp. That's the point where x prime and y prime are simultaneously 0. So this is the sort of thing that can happen. Okay. And now, if you look at the second one is interesting. The second one, if you think about what number 2 says, you know, y is just 2x, right? Number 2, y is equal to 2x, okay? It's actually just a straight line, so why not smooth? That's kind of weird. Like, what are we talking about not smooth? Well, it's a line, but it's not the whole line, right? Because x is just going to go between -1 and 1, because cosine goes between -1 and 1. And so it's actually just a segment of the line, and you just keep going back and forth, back and forth, back and forth between the two ends. And so those ends of the curve, the ends of the line segment, those are the points where it's not smooth. So you can have things like that happen, which are kind of funny. Okay, so, oops, I missed this. So, moving on. Smoothness, tangent lines. What's the connection, right? Well, it turns out that when you want to try to find the the equation for a tangent to a parametric curve, there's this nice formula that you get. Dy dx is, so we have y prime of t over x prime of t, just because my primes are not good there. Right, so y prime over x prime, that's dy dx. So that gives you the slope of the tangent line, and you know a point on the tangent line too, because you just plug the t value into the original parameterizations, right? X of t, y of t, and now you've got a point, you've got a slope, you've got enough information to get the tangent line. Okay, a few things to notice. We can find horizontal and vertical tangents this way, right? Horizontal tangent, we know dy dx should be 0, right? In this case, that means y prime is 0. So if y prime is 0, horizontal tangent. On the other hand, if x prime is 0, well, that's like a vertical tangent, right? Slope goes to infinity. The only thing is again, if x prime and y prime are simultaneously 0, well, then you get 0 over 0. You get an indeterminate form for the slope, right? And those are exactly the places where your curve might not be smooth, place where you might get those cusps, right? Sometimes you can use like L'Hopital's rule and a limit to still get a reasonable value for dy dx at those points, but not always. Okay. The other thing I just pointed out here, for those of you who do want to think in terms of vectors, one of the things that you can do is you have like some curve, right? So you've got this curve, and you think of the vector. All right, so here's your vector, x of t, y of t. And you calculate the derivative, you calculate x prime, y prime. And that actually gives you a tangent vector. X prime of t, y prime of t. And this is, in some ways, this is a much more natural way to think about it. It's just that at this point in the textbook, we don't assume that people have seen vectors before. Because, when the vector formulation, you treat x and y on equal footing. You don't have this relationship here, right? When we write dy dx, we're thinking of y is dependent on x. But not really. X and y are both dependent on t. They're not necessarily, we don't have that dependent relationship when we're dealing with parametric curves. So we're doing dy dx because that's what we're used to, right, from Calc 1, but it's not really the natural way to do this. The right way to do this is in terms of vectors, and you'll see that in Chapter 12. Well, if you look at Chapter 12, or if you take another calculus course, you'll see that in Calc 3. Okay? All right, let's do some examples, because I got to wrap things up in 10 minutes. I think we'll get there despite the annoying technical glitch. Very sorry about that again. So let's find equations of tangent lines. So for the first one, if we look at the first one, we have, so here's 1, 2. So for 1, so we do this. Dy dx is y prime of t over x prime of t. So y prime is 3t squared minus 1, just taking the derivative of y right here. X prime is just 2t. Okay? So at t is equal to 0, well, at t is equal to 0, we actually have a vertical tangent, right? Because if you try to plug in t is equal to 0, you get a 0 in the denominator. And so then we can say, well, what is, what's x of 0, y of 0? X of 0, we don't really need y of 0, but let's do it anyway. And when x is equal to 0, or when t is equal to 0, x is equal to minus 1, and y is equal to 0. So the tangent is, tangent line is simply x equals minus 1. It's a vertical tangent. If t is equal to 1, well then dy dx is going to be 3 minus 1, 2, over 2. It's 1. I get a slope of 1. And coordinates x of 1, y of 1. X of 1 is equal to 0. Y of 1 is also equal to 0. And so my tangent line is just going to be y is equal to x, right? Because the tangent's through the origin, slope 1, it's just plain old y is equal to x. Let me try to tackle the second one before we move on. So if x is equal to tan t, y is equal to secant t. Well, we've got to work a little harder on our derivatives this time, right? So dy dx, y prime over x prime. So y prime is going to be secant t tan t. X prime, derivative of tan, is secant squared. So I get tan t over secant t. So that's actually just sine of t, right? Tan is sine over cos, secant is 1 over cos, 1 over secant is cos. Yeah, tan times cos is sine, right? So at pi over 4, x is equal to tan of pi over 4, which is 1. Y is equal to secant pi over 4, which is root 2. And the slope is dy dx, which is sine at pi over 4, which is 1. Oops, 1 over root 2. And so the tangent, we get y is equal to the y coordinate, root 2, plus the slope, 1 over root 2, times x minus the x coordinate, the way you would normally do the equation of a tangent line. Okay, one more topic, 6 more minutes. We're going to get there. Thanks for those of you that stuck around. I see I've got most of you back. It's annoying that we had the glitch. I'll have to put this other link up on Moodle when we're done, but let's go. Area. The book doesn't do area, but I really wanted to talk about area. The thing that you can do with parametric curves is, so first of all, if you're just doing, eraser didn't work there. If your parametric curve is a graph, right? So if you just have something like x is equal to t, y is equal to f of t, right? And by the way, if you have a graph, this is how you parameterize a graph, right? Y is f of x, you just set x equal to t, y is equal to f of t, you've parameterized the graph. So if you think about area under a curve, right, and you think about, when you're doing the integral of f of x dx from like a to b, well, that becomes like the integral from a to b of f of t dt, right? And if you make some sort of change of variables so that x depends on t, right? If x is some g of t, then y will be f of g of t. And you get something that looks like this, right? Now, one of the things that you have to be mindful of is that frequently when we do parameterizations, you will find that as t increases, x actually decreases. And so you need a minus sign to compensate. That's this minus sign that you see here. And in particular, what happens is you have a lot of curves, a lot of parametric curves that are so-called closed curves. So you might have a curve that does something, like it goes around, and it does, something like that. And you want to find the area that's enclosed by that thing. Well, you can do it. You can use this sort of area integral to compute the area. You just got to figure out the starting and ending values for the parameter. And it turns out that if you travel in sort of a counterclockwise direction with that minus sign up front, you can go from the beginning of the curve to the ending of the curve, and somehow the signs all work out, things cancel, you actually get the honest to goodness area. It's a bit fiddly to prove why this works in every possible situation, but you can get it to work. If you go the other way around, so if you were going clockwise instead of counterclockwise, then you don't need that minus sign out front. Okay, and basically you just kind of want to think in terms of contributions to area, like y times dx, right? If y is positive and dx is negative, then you need that minus sign to get a positive area. Okay, so here are two examples, these two examples, and then we'll call it a day with 3 minutes left. For the ellipse, well, we talked about ellipses at the beginning. One of the things that's useful to know is that you can always parameterize an ellipse. Okay, you can always do this. You can always do x is equal to a cos t, y is equal to b sine t. Okay, with t from 0 to 2 pi, right? Because if you do x squared over a squared, you get cos squared. Y squared over b squared is sine squared. Sine squared plus cos squared is 1. Parameterizes the ellipse, okay? And so the area looks like this. The area would be minus the integral from 0 to 2 pi of y prime of t, sorry, just y of t, x prime of t, dt. So that's the integral from 0, minus integral from 0 to 2 pi of b sine t. Now the derivative for x, right, x prime is going to be minus a sine t dt, right? So double negative, positive, we get ab times the integral from 0 to 2 pi of sine squared t dt. Okay, and sine squared, usual half angle identity, right? This is going to be ab integral from 0 to 2 pi of 1 minus cos 2t over 2. And so you do the integral, the antiderivative for cos gives you sine. Sine vanishes at 0 and 2 pi. So that doesn't contribute. You get 1/2 times 2 pi. You get pi. So you get pi AB. There's a formula for the area of ellipse. Notice if A is equal to B, that's the area of a circle, right? That's the usual circle formula, pi A squared. For the other one, I got 1 minute left, so I'm going to leave you to try it. The other one, you get a curve that looks like this. I'm going to draw it for you. This one is done in the textbook. The book does arc length for this. I'm not going to worry too much about arc length. It goes around like that. If you check, and you can check the direction of travel by plugging in some parameter values, and you'll find that it goes in and it goes around this way. It actually goes around clockwise. So for 2, you got to be kind of careful, but the area should be, because it goes clockwise through the loop, you'll be a plus sign out front. You can check that the loop begins when t is equal to -1. You gotta check that. Check that the loop ends at +1, and then you do the same thing. Y of t, x prime of t, dt. That plus sign looks like a t. I'm going to get rid of it. You should get something that looks like that. All right, we're out of time. I'm going to end the stream here. I guess it's 2 streams. Sorry about the loss of connection in the middle. I hope it doesn't happen too often. We'll see how this goes. And oh, a note on the quiz. Right, yes, for that quiz question, right, y should be b times sine t. Should do it. If it doesn't work, I think the feedback buttons are still working in there for the quizzes, but it should be just whatever b is, right, times sine t. Make sure that you're taking the square root of the number on the bottom. If if it's not working, send me an email. I'll check to see what's going wrong. Okay. Yeah, that's most of parametric calculus. We didn't do arc length. We'll talk about arc length for polar curves next time. I think we'll do it then. Yeah, we're out of time for today. There's videos in the book, right? I managed to get right before they shut us down. Very last day the university was open, I did the last batch of videos. So we have videos up for parametric curves, polar coordinates in the textbook. So if you need more, go to the book, watch those videos. You can find those on my YouTube channel as well. There's playlists for it. So yeah, hopefully that works, and we'll see you all on Thursday. I'll try to have an office hour tomorrow afternoon as well, if anyone needs it. We'll schedule something through Zoom. I'll throw a link up for that in a bit. All right, thanks everyone. I'm going to end the stream for real this time. And yeah, sorry that was a bit of a mess. Okay.